come to the interaction of charged particles. Earlier discussions we had considered interaction of charged particles with some electromagnetic field represented by say A mu. Charged particle represented by wave function phi, and we had written that the equation, Klein-Gordon equation satisfied by this charged particle then is dou mu plus m square phi plus v phi is equal to 0, where m is the mass of the particle corresponding to the wave function phi, and v is the potential due to the electromagnetic field, which can be written as v equal to minus I e dou mu a mu plus a mu dou mu minus e square a mu a mu. Then we said the transition amplitude is in minus I integral j mu a mu d4 x, where j mu is the 4 vector current of due to the particle, minus I e phi f star dou mu phi I minus dou mu phi f star phi I, where phi I denotes the wave function of the particle before the interaction, phi f denotes the wave function of the particle after the interaction. E is the electric charge. Pictorially, this can be written as a current J mu interacting with an electromagnetic field represented by A mu. In particular, this A mu could be due to another charged particle. In that case, we can associate A mu with this new charged particle, and let us say A mu is the electric field due to that charged particle, and therefore, Maxwell's equation will tell you that box square A mu equal to J mu, where this J mu is not the earlier current, but this is the second current due to which the first current, charge current or the first particle sees an electromagnetic field A mu. In this case, we can, if you write A mu as epsilon mu function of q e power minus I q x, then box square A mu is essentially minus q square A mu. But then now we also have del square A mu equal to J2 mu. Together we then can say that A mu is minus 1 over q square J mu. If you observe carefully, or if you are careful with our earlier interpretations of q square in the Maxwell's equation, the way we had written q square equal to, we had q square equal to 0 for that case, which represents a photon. But now here if we take q square equal to 0, this will not work out, there will not be any current. Q square equal to 0 works for 0 current. That is, if you put J2 mu equal to 0, then it is okay. 0 by 0 in the limit, you will get some mu. We will not take that. So, what happens to the mass of the photon? Remember, we are not having a free electromagnetic field. So, it is not a free photon which is propagating. Free photons will satisfy q square equal to 0 or mass is equal to 0. But in the presence of matter, or in when it is interacting with other things, it can have an effective mass, either an effective positive mass, or it can even have a negative. It can be interpreted as taking away energy from the system or giving the energy to the system. And remember also that we are working with quantum mechanics, which allows us to violate even the energy conservation as long as it happens for a short period of time, because delta E delta t is approximately equal to h, or it should be larger than or equal to x for any transformation. So, you can actually give some energy to some particular system in a very short time from a massive particle, and then can remain mass less than the earlier original actual mass of the particle for a short period of time, as long as the uncertainty principle allows you to do that. It's actually, it is going the other way around. It says that we will not really be able to measure such deficits or such other things. So, this is one way of when we actually try to interpret it in that way, and then the possible confusion is that q square was taken to be 0 earlier when we associated that with A, and then why is it not 0 here, understood in this fashion. That when photon is interacting with matter, or when we are considering the photon associated with a charged particle, then we do not really cannot take q square equal to 0 for that particle. Rather, a mu there is then minus 1 over q square j2 mu, which is the current associated with that particle. Now, look at T f I, it is minus I j1 mu a mu d4 x, which is equal to j1 mu minus 1 over q square j2 mu d4 x. That is, there is a j1 mu interacting with another current j2 mu. Interaction is facilitated by transfer of something, say the photon, and I can actually write the same T f I as we already know by raising the index on j2 mu. So, j2 nu I want to write, but then I should have a g mu nu, so that everything is proper integrated over 4 position coordinates. So, I will take it as integral j1 mu. Let me take this g mu nu with this q square and write it as g mu nu minus g mu nu over q square j2 nu. Now, look at the picture again. So, we have a current j1 mu interacting with another current j2 nu through exchange of something which is represented by g mu nu over q square. So, these are two currents j1 and j2, and the other one, the factor, is basically propagation of the effect of j2 as far as j1 is concerned. When j1 looks at it, it sees the effect of j2 propagated to j1, and the factor corresponding to that coming in the transformation matrix transition probability is minus g mu nu over q square. We call this the propagator factor. So, we have in TFI a current interacting with another current, a current J1 interacting with another current J2 through a propagator, and you sum over all the possible values of x corresponding to this, and then that will give you the transition amplitude. I can actually say that, okay, let me do it in a proper way. At a particular point, corresponding to that, I have a nu and another point. Corresponding to that, I have an index mu, and this is j mu and this is j nu. And so, the propagator propagates from some point to another point, and if the indices are nu and mu, the momentum associated with that momentum transfer, which means momentum that the propagator carries is q, then the factor associated with that is g mu nu over q square. Okay. This is one way of diagrammatically representing it. It gives us a feeling that we understand clearly what is happening there. But I would advise that you should take it not as a real picture or realistic case in that sense. This is only an aid to get a feeling, get an understanding of what might be going on. But in quantum picture, you cannot actually trace the particle perfectly as in a path, therefore a current. It is a very hazy picture in quantum case, and then it is not possible to actually think about a particular time a photon is emitted by something and absorbed by a particle, etc. But but that does not say that what we are discussing is a half cooked idea. It incorporates this uncertainty in it. So, when we actually look at the transition probability, it says the probability for the transition to occur in quantum mechanics. In a particular interaction case, it may or may not happen, one thing. Second thing is that the expression itself is tight and mathematically correct up to whatever order of perturbation that we are considering. It is only that the way we want to see it, perceive this thing, picturize this in our mind by actually looking at as if a particle is going in a current and a wiggled photon emitted by that, which is absorbed by, which is interacting with another particle current, etc., is not completely in that way. There are a lot of issues with that, and then therefore, you should take it in that spirit. Okay. So, I just mentioned this because one should not go away with a wrong picture of what is happening there as such. So, it is only a pictorial aid to let us write down the expression, for example, correct expressions for the transition amplitudes in this case. Okay. Although we call it by the propagator, the current, etc. So, all these things are understood in that sense. Let us come to a more proper understanding. Let us consider j mu 1. I can write it as minus I e phi f star dou mu phi I minus dou mu phi f star phi I. So, this is the current due to a particle. Let us say this is the interaction point. So, before that is phi I. Let me associate a momentum to that particle as P A, and at the end, after the interaction, it is represented by phi f. Let us say the momentum is P B. So, the current that we are talking about is J1 mu is this. Now, consider phi I equal to some normalization exponential minus I p a x. So, we have considered a plane wave solution. Plane wave solution, the box normalization or some appropriate normalization has to be considered. We have to constrain the whole thing in a finite volume in that sense. So, N A is the normalization constant, P A is the momentum associated with this thing, and phi f similarly is N B e power minus I p b x, and dou mu phi I is equal to minus I p a mu N A exponential minus I p a x, and dou mu phi f star is equal to plus I p b plus, because it is the phi star that I will consider, not phi, N b e power minus, not minus, plus I p b x. Putting this together, J1 mu is equal to minus I e dou mu phi star phi f star dou mu phi I. So, dou mu phi I is actually equal to minus I p a phi I, and dou mu f phi f star is plus I p b phi f star. So, J mu is equal to phi f star minus I p a phi I minus plus I p b phi star phi I. This is equal to minus I, it is minus E, then I have p a phi f star phi I, second term I have a minus I and minus I, that is what is taken out. So, it is plus p b phi f star phi I, which is equal to minus E p a plus p b phi f star phi I. Now, this is equal to minus E p a plus p b n a n b e power minus I p a x e power plus I p b x, or I can write it as minus E p a plus p b n a n b e power minus I p a minus p b x. So, that is the current that I have here. J 2, so this was J 1 and J 2 nu. Let us consider this to be some chi I initially with momentum p c and chi f with momentum p d. In that case, J 2 nu in a exactly similar fashion as the J 1 mu can be written as minus E p c plus p d n c n d e power minus I p c minus p d x, where chi I p c is equal to n c e power minus I p c x, and chi f p d, the final state, is n d e power minus I p d x. So, we have J 1 and J 2 putting together in transition amplitude T f I, this gives us minus I J 1 mu minus g mu nu over q square J2 nu d4 x. This is our transition amplitude, where q is essentially the momentum transfer. So, that is, let us say, from the point of view of the current 1, particle 1, it is P A minus P B, the 4 momentum transfer. And in terms of the wave function explicitly written, we have integral minus E n A n B P A plus P B e power P B mu. All right. So, in all these cases there is a mu which is missing. So, I should be okay. Similarly, for J2 there is a nu there, e power minus I P A minus P B E x times minus G mu nu over q square, then the other current minus E n C n D P C plus P D nu e power minus I P C minus P D x integrated over 4 volume d 4 x. This is the transition amplitude written now in terms of the wave function explicitly written as a function of the momentum and the position. Now, let me do some simplification. Firstly, there is a minus I n A n B n C n D integral E P A plus P B mu minus G mu nu over q square E P C plus P D nu. None of this depend on the position. So, integration comes out of the integral. Integral exponential minus I P A plus P C minus P B minus P D x d 4 x. What is integral e power minus I P x d x minus infinity to plus infinity full range. This is nothing but the Dirac delta function. Now, if I have more than one variable, I can write e power, say, 3 dimensional case p dot x d 3 x, I will write it as exponential minus I p 1 x plus p 2 y plus p 3 z dx dy dz. So, each of these are independent of each other. So, I can take it as integral e power minus I p 1 x dx integral e power minus I p 2 y dy integral e power minus I p 3 z dz dz. This is equal to, first one is the delta function 2 pi delta p 1, 2 pi delta p 2, 2 pi delta p 3. Together as a compact notation, I can write it as 2 power 3 delta 3 vector p. This meaning of the last line is actually explicit form, in the explicit form, the line just before that. In a similar fashion, look at what we have in TFI. The last line, integral e power minus I p a plus p c minus p b plus p d, that can be taken as some single entity q or some capital Q or whatever as a momentum, combination of something, and then total together is a 4 momentum. times or dotted with x d4x. So, that is essentially a delta function minus I P A plus P C minus P B minus P D x d4 x, where now x is the 4 momentum 4 vector x, x0, x1, x2, x3 or x0, x, y, z, all of this together. So, we have 2 pi 4 delta 4 dimension P A plus P C minus P B minus P D. This actually means that 2 pi 4 one delta function says P A 0 plus P Z 0, P B 0, P D 0 and another delta function for P A 1, P C 1, P B 1 minus P D 1 into delta P A 2 plus P C 2 minus P B 2 minus P D 2 into delta P A 3 plus P C 3 minus P B 3 minus P D. With that, we can write T F I as minus I N A N B N C N D minus I N A N B N C N D. Then you have E P A plus P B mu minus G mu nu over Q square E times P C plus P D nu, and you have a 2 pi 4 delta 4 P A plus P C minus P B minus P D. So, we will write it as let me write it here, T F I equal to minus I N A N B N C N D delta 4 P A plus P C minus P B minus P D into M, where M is equal to E P A plus P B mu minus G mu nu over Q square E P C plus P D. Let us stare at it for some time. What is this? This is the transition amplitude for a particular interaction given by particle with momentum P A going to a particle with momentum P B by after interaction with a particle, another particle with momentum P C and going, which will go to a particle with momentum P D. Charges on each of these particles E. So, and the momentum transfer is Q. This then says that and N A, N B, N C, N D are the normalizations associated with that. We will come to that. Look at M. It is a Lorentz invariant quantity, as we said. This is the dot product between P A plus P B and P C plus P D with a Q square, which anyway is invariant under Lorentz transformation, and E square, which is again invariant under this. So, the first part E P A plus P B nu is associated with the first current, particle current. Second part is in the bracket G mu nu over Q square is associated with the propagator, and the last part E P C plus P D nu is associated with the third the current due to the second particle. That is one part. Essentially, that summarizes all the dynamics in it. What it is, it will give you the charge current interaction. Two charged particles, the currents of two particles are interacting with each other. Now, the rest of it in TFI is, one is the normalization factor, it is a factor of minus I also. Apart from that, there is a delta function. What does the delta function tell you? When you actually put it in the cross section, as we will do in a moment in the next class as such. So, when we put it in the cross section and try to find the number of particles which are coming out, etc., then we will have to integrate it over the momenta. When we do that, immediately we realize, because of the y function, the delta function, that when you integrate over all the momentum, Pa plus Pc is equal to Pb plus Pd. That is because of the delta function. And what does that tell you? So, the delta for Pa plus Pc minus Pb minus Pd tells us that Pa plus Pc is equal to Pb plus Pd. What is Pa? It is essentially the initial momentum of the one particle, okay, and Pc is the initial momentum of the other particle. So, if I write it in components, these are 4 momenta. I will get Pa0 plus Pc0 is equal to Pb0 plus Pd0, or essentially when you consider the 4 momenta, this is energy of the particle A plus energy of the particle C is equal to energy of the particle B plus energy of the particle D. When I said particle D, I mean the corresponding particle in the final state, the second particle in the final state. What is this? This is basically that the sum of the initial energy is equal to sum of the final energy. This is the statement of energy conservation. Similarly, when we look at the 3 momentum, Pa plus Pc is equal to Pb plus Pd. The sum of the initial 3 momenta equal to sum of the final 3 momenta. So, this is the linear momentum conservation. So, the delta function makes sure that the energy of the initial particle, sum of the initial energies is equal to sum of the initial final energies, energy is conserved, and similarly Lorentz the linear momentum is conserved. And that only talks about the kinematics, that the energy momentum conservation, that part. The rest of it, all the dynamics is in the quantity m, and m is called a Lorentz invariant transition amplitude, and we should see that note that when we consider this charged particle, okay, initially we have not considered anything, any information about this particle other than its momentum and charge. We have in fact represented the particle by a wave function phi I equal to n a e power minus I p a x. It has a momentum, okay. It has some charge associated with that is understood, but supposing we consider it as an electron, then what about the spin of this particle? And the underlying equation that we considered was Maxwell's equation, and even before that, the Klein-Gordon equation. And we will see that here with the Klein-Gordon equation satisfied by the particle phi, we do not have any provision to discuss the spin of the particle. So, if we want to incorporate the spin of the particle or information related to the spin of the particle, then we will have to modify this and find out slightly different way of dealing with these particles. That is one thing that we will have to understand, and then we will come to. The other thing that we have not discussed is what are these normalization constant, and then how does it, I mean what at least what are the ways to look at it, how does it come in the picture. In the transition amplitude they apparently appear, but then it should be independent of this normalization as such, the transition amplitude. How does that come about? Actually, we will see that we can relate this transition amplitude to the cross section, and the cross section which actually tells you directly, which can be directly related to the probability for finding a particle scattered into a particular region, etc. We will be independent of all these normalizations, and we will see how that comes out in the next class.